Well, good morning, everyone, and welcome to WEC's Reliability in the West discussion series. Today is the 6th day of March 2024. It is 11 a.m. We're going to start by, I'll introduce myself real quickly. I'm Travis English, WEC Senior Training and Outreach Specialist. We'll start by taking a look at our antitrust policy. All WEC meetings are conducted in accordance with the WEC antitrust policy and the NERC antitrust compliance guidelines. All participants must comply with policy and guidelines. This meeting is public. Confidential or proprietary information should not be discussed in the open session. This webinar is also being recorded and it will be posted publicly. By participating, give your consent for your name, voice, image, and likeness to be included in that recording. WEC strives to ensure the information presented today is accurate and reflects the views of WEC. However, all interpretations and positions are subject to change. If you have any questions, contact our legal counsel. I'm going to take a look at some upcoming events that we'll be having here at WEC. We'll have the Reliability and Security workshop in Salt Lake City. That's coming up in a few short weeks here. And this is a compliance-based training. Excited to have it here in Salt Lake. We'll share some information on how to get registered for that in the chat. This event coincides with that Reliability and Security workshop. It's our enforcement fundamentals. This is the first time that we've hosted it in person here at our Salt Lake City offices. So this is going to be on that Monday, March 25th. Some more information in the chat on how to join that training as well. With that, I'm going to take a look at today's inverter-based resources grid forming technology panel. Really excited to have Julia Matavosian, Chief Engineer at ESIG, or Energy Systems Integration Group. Ryan Quint is back. If you tuned in last month, he's back. He is the founder and CEO of Elevate Energy Consulting. And then we have Song Wang, the Senior Principal Engineer at Portland General Electric. So with that, I would like to bring in Victoria Ravenscroft to give us just a quick update on the series itself and IBRs. Victoria, take it away.
Great. Well, welcome everybody. It's good to be back again. Last month we started our discussion series for the year with the topic of inverter-based resources. And we took a look at ride-through capability and some of the issues that we've had in ride-through capability in past events. Today, we're going to continue the inverter-based resources discussion, but we're going to turn our sights to the horizon and talk about some of the future technology in inverter-based resources, specifically grid forming technology, and talk a little bit about and hear from our panel on what the potential role in the future IBR fleet grid forming technology might hold and what that might mean for reliability. So we've got a great panel lined up, but first I'm going to turn it over to Julia from ESIG to walk us through a little bit of information about what grid forming technology is, just to kind of set the stage for us on that a little bit. So with that, Travis, I'm going to turn it over to Julia.
Great. And Julia, I believe you're going to grab the ball to share your slides.
Yes, that's correct.
Great.
Let me share. Full screen and right. Let me know if you can see my screen.
It's perfect. Thanks, Julia.
All right. And let me grab the pointer right away so I don't get distracted by it. All right. Good morning, everyone, and thanks for having me on this panel. I'll start with this little cartoon, and I'm really happy to know that IBR is a common term here, so I don't need to go into that and explain anymore. But yeah, IBR, inverter-based resources, meaning solar, wind, and storage. So I'll use IBR throughout my introductory slides. So I'll start with this cartoon here, and on the left-hand side, imagine there is 0% of IBRs on the grid, and it's a strong grid, and it has synchronous generators such as coal-fired, gas-fired generation, hydro generation. And then on the right-hand side, we were at the other side of the extreme at 100% of IBR, and it's a weak grid, and it can have potentially instability issues. So as we getting into this maybe 10 to 20% of IBRs, and you talked about it in the last panel, as I understand, we cannot longer let them trip offline during faults. So they need to have fault right-through capabilities. So we start requiring this from IBRs at this early stage of IBR penetration. And then as we get to higher levels of IBR, then not only they need to stay online during faults, but they also need to provide some supporting functionalities for the grid, such as frequency support and voltage support in other ancillary services. So as we get to even higher shares of IBRs, if we don't have IBRs to provide even further control advancements, then other options to ensure stability is to keep conventional generation online. So basically keep synchronous generation to support and provide some of the grid supporting functions on the grid, or build additional transmission equipment to provide stability to the grid. And so basically, in the absence of advanced controls from inverter-based resources, there is a limit of how much renewables can be installed on the grid and still maintain stable grid. However, keeping conventional fossil fuel generation online leads to high renewable curtailment, and also additional stabilizing grid equipment is expensive and time-consuming to install, and in the meantime, again, you will have to curtail renewables. So now going to what's grid following and what's grid forming and what's the difference. I have this cartoon again here with the people that are following the leader. So majority of inverter-based resources today are grid following. They read voltage and frequency of the grid, and then they lock onto that and inject power aligned with that grid signal. And that grid signal today comes from conventional synchronous generators. It just kind of by the way the grid was designed and by the way synchronous generators were designed over time. The further the pockets of inverter-based resources are from synchronous generators, the weaker the grid. And in my previous slide, I had this weak grid notion when you have a lot of IBRs. What it means then is that signal that IBRs need to lock onto is easily perturbed by power injections from the IBRs themselves. And so it's making it hard for IBRs to lock onto it correctly. So basically IBRs are kind of distorting the signal for themselves, and it becomes harder for them to inject power which is aligned with the grid signal. And this may lead to local instability issues. So grid forming inverters is kind of advanced control strategies for inverter-based resources that create local voltage and frequency and oppose changes inherently injecting needed amount of power to the grid. This can have stabilizing effect on the grid, and it can also support islanded operations. So for example, if the grid splits into smaller islands and they still can operate stably and reliably, and providing black start capability, but this requires special design considerations for an IBR that are above and beyond just overall interconnected grid operation. So deploying this grid forming capability, so this advanced control capability in IBRs, especially in batteries, is cheaper and faster than adding new stabilizing grid assets. And the new stabilizing grid assets also require additional investments and take longer time to build. So what we need to do to kind of pass this threshold and achieve higher shares of inverter-based resources is identify what system actually needs, identify advanced controls or grid forming controls of inverter-based resources and what capabilities are needed, and then produce and deploy IBRs with needed capabilities and also disseminate lessons learned. So I think we're kind of finding ourselves between this second and fourth step here. So why battery? I spoke about, batteries, lower hanging fruit for grid forming deployment. First of all, to provide some of this grid forming functionalities, there needs to be energy buffer. So battery then naturally comes as the first provider of grid farming capability. And also, if you look at the queues today, there are 680 gigawatts of battery in the queues. And I also looked in this queued up analysis from LBNL, and actually about 270 gigawatts of this comes from non-ISO areas in the West, and 120 gigawatts in CAISO. So large portion of the 680 gigawatts is actually in the West. And I have on the right-hand side, and these two documents are linked up where to great lengths these documents talk about benefits of grid forming capabilities, but also specifically why battery is a lower hanging fruit and why deploying it in the batteries makes sense. Yeah, but basically to say grid forming capability requires energy buffer. It's already available in a battery. Its controls can be easily implemented in a battery resource, and we already have a lot of battery resources in the queue. If you look at what's already installed in the world today, I have this list of different batteries. In the US, it's currently only in Hawaii for grid-connected applications, but there is also a number of industrial black start and microgrid applications on the mainland US. Here I only have listed grid-connected applications, and there is more to come in Australia currently, where they are deploying about 2 gigawatts of grid-forming batteries by 2025. Coming back to the US, NERC Inverter-based Resource Performance Subcommittee recently published this grid forming specification. This was geared towards areas that are already on the path of deploying grid forming capability in batteries, and kind of to provide some guidance for these areas. The key takeaways from these documents is that grid forming controls are commercially available in BPS connected BESS, and this can be implemented in standalone or hybrid applications at very small incremental project costs. All new battery storage should be designed and commissioned in grid forming with grid forming capabilities because they provide additional stabilizing characteristics, and we should take advantage of this fleeting window of opportunity that we have today. As any other resource, it requires studies to make sure that it stably operates on the grid and requires testing against grid forming functional specifications, requires also more detailed EMT studies. Just to mention, ORCOT and MISO already taking first steps. In summer 2023, ORCOT ran a study evaluating benefits of grid forming inverter-based resources for ORCOT grid, specifically looking at West Texas, and results indicated that grid forming IBRs could be a viable option to improve system stability and also reduce congestion from the West. Currently, they are working on grid forming IBR requirements, including but not limited to performance models and studies and verification requirements, and they expected to publish this by beginning of summer 2024. MISO is also taking similar steps. They are currently gathering background information of grid forming IBR capabilities and specification practices around the world. And they are working with stakeholders to develop grid forming performance requirements. Again, kind of similar vein as ERCOT, and expect those by the end of 2024. And so just to conclude, I wanted to bring up this statement from Andrew Isaacs from Electronics that he presented at E6 special topic workshop on grid forming IBRs that we had in June 2022, so almost 1.5 years ago. The motivation he brought up, I think, is very sound. He says, look at Hawaii. There are a number of fragile islanded systems. They are seeing really high shares of IBRs already today, and they need to rely on grid forming technology kind of already implemented in the field and rely on it for reliability of the grid and also to prevent blackouts and even to provide black start. This technology is already on sale with little marginal cost for batteries. So North America shouldn't wait and see what happens in Hawaii, but rather try to procure grid-forming batteries today, test it out in the field, gain knowledge and experience with this technology before we actually need to rely on them for, grid-wide reliability and black start. So we have this time that Hawaii doesn't have, and we should start now. So with that, I'm ready for a panel and questions. Looking forward to it. Thank you.
Thank you so much, Julia. I know that was a lot of information that you were trying to get through in a very short amount of time, a short window we gave you at the beginning, but you did a great job getting through it. If Ryan and Song can also come on the camera, we would like to have a panel discussion with everyone now. And I would remind any of the people who have logged on to listen to the discussion to go ahead and put questions in the chat. And then Victoria and I will try and field those questions as we go along in this discussion. So part of what I learned as we've been doing this series on IBRs is that there's not a ton of grid forming IBRs within North America right now. And Song, can you speak to what Portland General Electric is doing right now with regard to grid forming inverter technology?
Can you hear me?
Yes.
Yeah. So as Julia mentioned in her slide, we can see in the current situation is Australia and Europe are both in full swing on grid forming. But in US, basically there is no grid forming deployment. But this is also why we're here to talk about this question. So I want to take this opportunity to introduce a DOE demonstration project we're currently working on. So this project is started from last October, and that is DOE funded 4.5 million, and all the participate partner share $5 million. So on a demonstrate reforming technology. So we are going to use our Whitridge renewable energy facility. This facility located at the northeast part of Oregon. It is the first of its scale, 380 megawatts wind, solar, and battery combined renewable power plant in North America. And so our plan is to upgrade portion of the type 3 wind to grid forming, and then we add additional grid forming battery, and then further we will upgrade the power plant controller to be able to control both grid forming and grid forming. So this is a 3 years project. We split by a 2 period. So first period is a preparation period for 21 months. So in this period, we will identify the performance metrics. So the purpose for this, one of the purpose for this is to verify the project success. And another purpose, this could be, this document could be a reference for future standard development, especially for the interconnection study. In addition, we want to do the software and the hardware simulation to ensure the control logic is correct when we upgrade to a grid forming. And then there will be no impact to the turbine itself, because the upgrade to the new grid forming response to voltage and frequency is much faster than the grid forming. And also we want to make sure inside of the power plant there is no interaction, and also in nearby power plant no that interaction as well. This is also include the system interconnection study to ensure the definition we made for the performance metrics is reasonable. And to do all of this, we also need to develop a appropriate generic model that include the new power plant controller and type 3 being the generic grid forming model. IBRs have already developed a 2 grid forming model. One is a Joule-based grid forming model. One is virtual synchronous machine model. Those model developed the perfect fit for the battery and the PV, but there is no grid forming model for type 3 turbine yet. In addition, in this period, we also will do the engineering design and the substation modification. And after that, everything is right. We got go, no go decision, and we go to the next stage, which is demonstration stage. And then we will do the voltage frequency regulation, such a grid service. And then black start, islanding, and cost balances, and then the knowledge sharing. So we hope by doing this project, we can answer some industry questions about the grid forming deployment. So that's basically about this project. And if anybody want to know more detail, you can directly contact me.
Thank you, Song, for going through some of the details of that. Ryan, I want to get you into this conversation too. I know you have a vast knowledge on this subject matter, and I know from what we've talked about previously, we've got the spectrum, right? I appreciate Julia's sense of urgency to get this technology on the grid when it seems to have so many benefits, and yet there's not a ton of it yet. And with what Song was just telling us about how Portland General Electric has this phased in approach, what are your feelings on where we're at with this grid forming technology right now, and how fast we maybe need to deploy in order to maintain reliability of the grid?
That's a good question, Chris. And I think the PG project and the partners that they have is a really impressive project. They've sort of taken one of the most complicated power plants in the country and added on a vast additional complication. So it's a great R&D exercise, right? To take 3 different technologies, wind, solar, batteries, try to add grid forming to the whole package and see if that works, right? So that's important to sort of caveat at a high level, is that degree of complexity is orders of magnitude. And I think a standard rollout of a grid forming device that's, say, a standalone battery, right? And that's what I think the difference you hear between Julia's message, which I very much align with. We should be doing this already, and I think we're behind. Every time we connect a battery that's not operating in grid forming mode, it is an incremental added cost to ratepayers in the end. And nobody wants that, yet when you look around, there's no action being taken. So something is broken, right? And I think that everyone is recognizing that. And now it's turning to, well, what do we do about that, right? The technology is here. It's been deployed. We actually have grid forming in the United States. It's a small little project out in Cape Cod, 13-mile single line feeding the Cape Cod Peninsula on a 23 kV system. It's a small little project, but they realize we're in an ultra weak grid condition when lines start to trip during hurricanes. And so rather than our entire peninsula going out and losing power, we'll build a grid forming battery out there that can sustain that portion of the grid for an extended period of time in the event that that line disappears, right? Which is fundamentally what grid forming is really useful for, right? That is fundamentally the test in the NERC document that Julie and I and the team came up with. Can you survive operating in an IBR dominated or 100% IBR grid? And that's fundamentally the test used around the world, is your grid forming if you can handle that, right? And it's almost as simple as that. So I think we're beyond, there's still a lot of R&D that can go into, widespread adoption, but we are at this point where we've gone from a technology readiness level, for those familiar with that, like we're past 9. Like the 9 is the highest level in technology readiness level. We're 9++++. It's been deployed around the world, proven wildly successful, like saved the Australian grid in certain areas, right? Being deployed in the UK and other areas. And now we're in this sort of like grid readiness level, something that we're coming up with at Elevate, where we're at grid readiness level 1, right? We're back to the beginning in terms of systems integration and systems deployment. And we're starting to see momentum coming with MISO, with ERCOT, with some of the other utilities, starting to adopt the requirements. And I know like groups like Unify, for example, large DOE funded project are asking these pertinent questions of, well, how do we accelerate this? We need to accelerate it. We all the industry experts recognize we need to accelerate it. So what are the barriers towards widespread adoption? And I think it ultimately comes down to kind of a little bit of how do we go about doing it? Utilities are asking, like, how do I create these requirements? How do I run the studies? How do I either demand, require, or incentivize for it? And those are sort of the obstacles or barriers facing us right now, is much more on like the systems integration side. But we continue to kind of beat the drum that the technology is here, and it provides these like essentially useful grid stabilizing attributes that the NERC Essential Reliabilities Task Force 5-7 years ago didn't really think about this kind of stuff. And it's not a knock on that. It's the fact that the grid is evolving at such a rapid pace that wasn't even a thought 5-7 years ago. And now it's a technology that's readily available and will probably be entirely evolved in the next 10 years from now. But that shouldn't keep us from jumping in and sort of jumping on board to get those grid stabilizing attributes for the system. So I'll pause there.
Thanks, Ryan. Oh, so to your point about jumping in, I'm going to go to Julia and ask for the barriers that Ryan was talking about there, and you addressed some in your slides: lack of models, experience, lack of requirements. What do we do about those? Right? We're in a field. Energy is a field where it has historically moved slowly, and those technologies and getting new technology on the grid has historically been an iterative process to make sure that we're not doing something to destabilize. How do we get past those barriers in order to utilize, to Ryan's point, about dollars, to make sure that we're putting the dollars where they need to be now?
Yeah, so I guess take your first question first about barriers, and then I'll take another question about what happens if you don't do it and kind of where the dollars go then. So the first one is, I think the developers for the plants, they will only develop the requirements that are there. So unless there is either requirement, specification that system operator wants, or there is some market product that incentivizes, they will just build to a minimum requirement that exists today. And so that's what we are seeing. Nobody were taking incentive to build grid forming. There is also, it's not even incentive, there is also in some areas, anecdotally, you hear stories that there is a barrier because, say, some system operators only use generic models, only accept generic models. And until very recently, there was no generic model for grid forming battery. So there is even this kind of administrative barrier that they cannot supply a model that system operator would accept for the study, even if they would like to implement grid forming capabilities. So there needs to be, I think the ORCAT and MISO are taking the right first step by identifying what the requirement should be. And then it gives a signal to developers that this will be capabilities that is required. They will go to manufacturers and ask for this type of products. So that's the first one, where I think the problem will be if we don't take this window of opportunity now, is that the more inverter-based resources we install, if they are still this old grid, not old, but current grid following technology, there will need to be supporting equipment on the grid. So either we need to keep synchronous generators, maybe that want to retire, we need to hold them longer online, and that will basically impose costs on the grid and to ratepayers, or we need to add additional equipment to the grid, such as synchronous condensers, maybe not transmission, more being able to push more megawatts, but transmission to ensure that the system is stable, provide system stability. And so all of this is expensive, whereas if you look at just installing resource itself, and a resource itself can provide some of these functionalities, then you don't need to pay extra for this resource to get connected. So I think there is a saving there for ratepayers that Ryan was talking about.
So that's a really important point that I want to emphasize, because I know we have a lot of policymakers that generally listen in on these discussions. And it looks like when you're adding technology and adding technology and adding technology, right, that there's a significant cost that goes along with that. But what I hear both you and Ryan and even Song touched on it a little bit, I think, is that by adding grid forming now, we'd actually be saving dollars to ratepayers in the long run, because we wouldn't have to be duplicating and sort of working across our own interests on those things.
Yeah,
Can
the
I jump in
supporting
there?
capability will come from the resource itself.
Can I jump in there, Chris? Is that okay?
Sure. Yeah, of course.
And I think the clarifying sort of caveat to that statement, which is it's a good overarching statement, right? Like doing it now has a lower, societal cost as opposed to waiting. And there's sort of 3 degrees of complexity that I'll explain, right? So grid forming in a wind resource is the furthest level of complexity. It's a spinning mass. There's a lot of complications around the turbine, and the controls and all that stuff that goes into that. But I was just on a call this morning with a very reputable OEM, just on an industry meeting, and they were talking about grid forming is here or coming for wind, right? But there's likely a cost associated with that. The next is solar, right? No moving parts, but you still have to have this sort of added energy buffer on the, sort of between the panels and the inverter. You have to have this built up stored energy to do the function of grid forming. And so there's some added complexity and or cost there, but it's less sensitive and complicated compared to wind. And the third easiest is batteries. And what we started this with what Julia was referring to, which was these project developers are proposing batteries, and unless they get incentivized, they're not going to turn it on because of these incremental costs. That was sort of the assumption. We've kind of gone deep with some of the OEMs, and at least one very large reputable OEM has said the incremental cost to installing a grid forming battery is $0. Right? It's free. It's just it's a setting. It's a button you push to turn on. There's all the associated costs associated with running studies, with making sure that it's reliably connecting to the grid, making sure it doesn't interact with other resources. But those costs are incurred regardless of whether you turn it on or off, because it's part of the interconnection process, right? So if you do it up front at the beginning of the interconnection process, there's 0 incremental cost. If you do it later and you want to retrofit, you're paying a consultant, probably $500,000 to go create the models, run the studies, work with the manufacturer, et cetera. It's very expensive, right? So that's really the fundamental point there. There was also that question of, well, okay, if there's added cost or complexity on the generators and they don't want to move until the generator owners, and they don't want to move until there's a requirement, why are transmission entities who also own batteries not moving on this right now? Right? The more money the transmission owner spends, the higher rate of return they get. You would think they would be incentivized to spend the extra money to get the dollars, right? Frankly put, right? They're still not moving, right? And that's what led to the NERC document, because what we heard from transmission service providers, transmission planners, was we don't know how to ask for it. We don't know how to specify it. And that's exactly what the NERC document is, which is now being used by hopefully by the MISOs and the ERCOTs and other system operators, is here's a sort of a toolbox or a tool to use in your toolbox on how to specify, how to ask for it, right? So we're trying to really fill in all the puzzle pieces to connect the dots to sort of have this clean runway to adoption, both for project developers and generator owners, because it's free for batteries, and for transmission owners who will see a noticeable like improvement in grid stabilizing features, which they eagerly desire, right? So it's advantageous for both sides. It's a win-win.
I appreciate the clarity on that, Ryan, and I really appreciate the intellectual honesty, because to say it's free, right, is a statement, and a lot of people, you get their ears perking up. And then of course there are dollars behind that for studies and other things. So I appreciate the balance with which you present that position. We have had questions come in from the moment that Julia started showing slides. So I'm going to let Victoria come in here and ask some of the questions that we've had coming in from the listeners.
Great. I'm going to try and synthesize several questions into one. We've been peppered with a lot of them, but I want to touch on something, Ryan, that you just mentioned, and it's been talked about throughout this, and that's the modeling and the analyses that are needed to do this. We know that NERC has done some work on the broad continent-wide level, and we know from what Song is saying that individual companies are looking at their own systems. Is there anything in between those two, and is that type of analysis, or the lack thereof, if it's lacking, is that something that's stopping the implementation? Is this we need more information kind of a situation? Can Ryan, I'm looking at you. You don't know that, but I'm looking at you maybe to start, and if the others wanted to weigh in on that question a little bit as well.
Sure, yeah, I can start and I'll be brief. And, I think we have a good mix of experts here, right? Julie's deeply knowledgeable on all of this, and Song is the chair of the WEC MVS group, right? And implicit, well, actually it's explicitly, but a lot of folks don't recognize this, right? FERC Order 901, which is sort of changing the NERC standards dramatically, mandates that the models that are used for studies be the models coming out of the WEC MVS. Right, so the entire nation's spotlight is now on WEC MVS to deliver exceptionally high quality models proactively, to ensure that we can connect resources. Right now, there are challenges, frankly, and Julia hinted at this, right? There's challenges with generic models being developed not by manufacturers, right? And manufacturers being sort of constrained or handcuffed by the the software developers in terms of their ability to get new models into the programs. It's a very complicated, messy environment over there, in the modeling world, right? So if I'm a project developer right now, I'm going, okay, I know I'm going to need to meet FERC Order 901 and the associated NERC requirements in 3 years for modeling. And so I have to have a generic grid forming model. Where is that model? Oh, it doesn't exist. So forget it. Not like discussion's over at that point, right? Because the model doesn't exist. I'm going to go with a technology where I have a model that I know will get me through the interconnection queue as swiftly and simply as possible, because that's all they want to do, right? Because that's the end game, is get through the queue, right? So if I've got a model that's going to run me into a bunch of complexities, I'm not going to go with that, right? And so that type of thing needs to be overcome like 3 years ago, realistically, right? Because we've been integrating IBRs for grid forming in other parts of the world for a few years now, right? So we're dramatically behind. And I think it comes down to WEC MVS is a voluntary activity, right? There is no funded entity or body in the United States, in North America, right, responsible for the creation of models with dedicated resources that can generate models rapidly and keep up to speed with the manufacturer's changes, right? Sort of be like an arbiter or ombudsman between the OEMs and their sensitive information and the utility industry. And WEC MVS does a tremendous job on a voluntary nature trying to do that, but at the speed in which everything is changing, that is essentially an impossible ask of Song. I don't want to put words in Song's mouth, but I can't even imagine the pressure on WEC MVS to do that. So
So Julia has her hand up. I'd like to go to Julia, but Song, I would like you to weigh in on this as well.
Sure.
Yeah, I would actually let Song go first, because I wanted to talk about generic model from WEC and MVS, but then I'll add a little bit about studies to what Victoria has asked.
Yeah, I just wanted to give a little bit background. Thank you, Ryan, bringing this up, and for the modeling development. So this is a long story. Back to 12 years ago, when we operate our system in Wyoming, and that is a relatively weak system, right? In there, 230 kV lots of wind and high penetration of renewables. And then we start to see these weird things, like just occasionally oscillation happen. We don't know why. And 6-7 years ago, we start to accept, to learn the grid forming, and start from there. We're thinking, oh, we need to develop a model for that once we learn that. And so we after that, we put a lot of effort. That's like 3-4 years effort on that. And then we developed a model based on that. We done lots of study. and we saw, hey, this is really a solution for the future. And then, so that's a little bit background, but I think there is another reason, add on Ryan's comments, was the, the reluctance from the utility to adopt the grid forming. I think one of the things is the risk aversion. When we look at when we see all the work we done in the past, all research, we saw this the good things for grid forming, but utility and the grid operators, they are typically risk averse due to the critical natures of the electricity grid. Adopting new technologies such as grid forming involves inherent risk related to the performance, reliability, and compatibility with the existing infrastructure. And utility just may reluctant to take this risk without sufficient evidence of the technology effectiveness and the reliability. So that's another reason we want to do this demonstration project to overcome that. The model definitely is important. We were working on that, and that's still effort. But I think there is another thing, just nature from the utility company.
So I love the phrase inherently risk averse. that is what I know to be true as well. Julia, did you want to chime in on that also?
Yeah, and I think I'm kind of starting to see, looking at ORCAD, MISO, maybe other areas, starting to see a clearer path of how these studies can be done. And I think there's no harm in doing a study, right? And so I think where people can start is with, there is now a generic grid forming model from WEC that's been approved and been developed by PNNL initially. There is a model developed by EPRI, also generic model that they would offer, and it has different types of grid forming control. So even that can be tested if system operator so wants, or transmission owner. And then so you start with generic models and you look at what are the benefits for the grid, kind of just to get general understanding. And then the next step is to go to manufacturers of grid forming batteries, if that batteries you are looking at. And they, under NDA, they readily offer, they're actually willing to deploy this technology and also get to the common grounds, what the specifications should be and what the requirements should be. So they will work with transmission owners, and I know for a fact they work with ORCAD, they offer to work with MISO. They will offer models of the equipment under NDA where transmission owner can test it out and see what are the benefits. And then that gives them confidence how this equipment is going to operate on the grid. Are there any issues? Do they need to kind of tighten the requirements and specifications on the end? So I think it's a good way to start with the study, look at the benefits, and then kind of get more specific on technology.
Yeah, baby steps still send us in the right direction, right? Ryan, I know you had something to say, and Song had his hand up too. I'm not sure which one was directly responsive to Julia.
Yeah,
I will directly address Julia. I think the grid forming inverter model, I just want everybody knows, since there is 150 people on this call. So the grid forming model for DUC-based already developed, approved by MVS, and the specification for the virtual synchronous machine-based model approved. And our goal is to approve that model entirely in May. So we will have some kind of a model, and all those models with NERC's help to get the OEM's comments on that. So it's more closer to the OEM's real control logic for those two. We're working with GE, we're working with Siemens, we're working with SMA for their, they provide feedback for this model. Recently, we're working with Tesla on the virtual synchronous machine model, just for information. Right?
Yeah, and Chris, I was just I'm glad Song went first. I was going to kind of bring it back to we have 150 people on the call, but I've learned in my past, 9 years prior at NERC that when you start talking about modeling, you lose like 85% of the room, and then the extra 15% are ultra excited about it, right? I think Julia hit on a fundamental point, though, that if you're involved in something like an integrated resource plan or something that's looking at, hey, I've got a policy of 100% renewables by 2035 or 2040 or 2050 or whatever, right? And you're running these production cost models or other, type of models that are looking at energy and capacity and those types of things, and you're not running a deep stability analysis of that future, you're driving yourself right off a cliff. Right. And so because the grid is, fundamentally, the grid will not remain stable with grid following technology out there at a pervasive level, right? And so we have to take fairly significant mitigating action to fix those stability problems, which tend to get overlooked by the policymakers, the decision makers, et cetera, until they're an immediate emergent reliability problem, and then we do anything we can to fix them, right? But it goes back to that, like, we can be very proactive in this process, right? So we should already be starting on the, sort of using some of these generic models that Song and MBS is putting together, running these scenario-based transmission planning approaches. 20 plus year scenario will be at 95% penetration, at least under some hours. That grid will not work with grid following only. Where do we put grid forming, and or where are you going to put a half dozen or a dozen synchronous condensers, which is going to be, 1,000x the cost? Right. So we really need to be running those studies and then pulling in the OEMs to update and improve the models as you sort of get closer to that reality.
And I think that I appreciate this conversation so much, because I think the decision makers and the people who approve, right, the cost recovery for this for the utilities, I understand the pull, much like your time at NERC, right? My time at the Idaho Commission as a commissioner, and considering recovery of costs for the utilities, at least investor-owned utilities at that time, is that that risk aversion is real because they're worried about recovery of costs, but they're dealing with economic regulators who are people who want the utilities to make decisions based on how much it's going to cost the ratepayers in the end. And so there is a broader conversation here that I think is so important, that because of that component, right? This is not just the newest, latest, greatest technology. This is a technology that can help with things that we've been trying to grapple with for a while. Black start, islanding, the cyber and physical risks to our grid right now. This would appear to be a technology that can be of really great assistance in all of those other considerations. So I do think that there's a balance that has to be met here for the risk aversion versus where we can get to based on the dollars, and getting something on the grid that could really help with a variety of issues that we've been grappling with for the last decade or so. I'm going to allow Victoria, I know has been, I don't know how she does it, but she pulls from like 8 questions that have been asked, and then she asks them all in one big question, and we're running out of time quickly. So I'm going to stop talking and let her ask.
Right. And this one, selfishly, I added my own part of it into it. So assuming that we want to see the future that I think you all are seeing, right, with grid forming technology as a part of our fleet, it's integrated. And thinking about sort of the chain of decisions and events that have to happen to make that future a reality. Where in that chain, and on which actors in that chain is the most effective place? Is there a single place that we can apply pressure to make this happen, or is this a more diffuse issue where we need to attack this on different fronts to make that future happen, assuming that's the future that we're after? And where might those pressure points be, the most effective pressure points on the chain?
I can jump in, I guess.
Please, yeah.
This one's I guess a sensitive question, so I'm glad you asked it, right? So that I think we've covered a lot of the sort of pain points or the chain there around going through the interconnection process, you have the generator's perspectives, the transition service provider's perspectives, who owns the battery. I'm going to focus on batteries alone because that technology is like ready to go. But sort of, yeah, that overarching question, like, why is this not happening? Right. And if you read the NERC reports, right, it's the same message, different topic. Like read all the dozens of NERC reports we put out over the years, and everything roots back to the interconnection requirements. It's as simple as that. You're not going to get the technology unless you have a requirement. And we're cautious about, like as an industry, we're cautious about over regulation. We're cautious about cost. These things are in the SARs, right? Explain the cost implications, right? But when you can say there are significant benefits and zero cost, right? It's a hard argument to make. But then the question comes back to all these things we've been talking about. Well, what about the models, and what about the performance settings, and how do you want me to control this thing? Those things come back to having and needing clear and effective interconnection requirements, right? And then if you read the next layer down of the recommendations in the NERC reports, you see that industry is not voluntarily adopting their own interconnection requirements. We are seeing progress there, MISO, ERCOT, right? We can highlight MISO and ERCOT all we want, but that's 2 out of 1,000 entities, right? So how do we get consistent, uniform progress in this area? Somebody needs to submit a SAR, right? The NERC, the latest NERC white paper that was approved and published by the RSTC also says all newly interconnecting battery energy storage should be grid forming capable and operational, right? We can make recommendations all we want. It's not doing anything, right? So the underlying item that was implicit and was not stated is somebody should submit a SAR to make that mandatory, right? Because it's zero cost, right? And so that'll bring some guiding light to making everybody sort of jump on the train, right? So that's my 2 cents, and I think it's a logical next step for us as an industry because of that zero incremental cost, right? If there was notable cost, to be a much more sensitive conversation around market incentives and all these other things. But for that one unique important factor, like just standardize it and let's move on.
Great answer. Julia or Song, do you agree? Is it?
I totally. Just one thing that I like, as we keep talking, this example just sits in my head, and I'll bring it up, and I think it's still relevant. So in 2009, ERCOT went, and I worked for ERCOT before 10 years, so it's like still in my head. 2009, ERCOT went out and put in requirements for inverter-based resources to provide frequency response and have capability to provide frequency response. It was way ahead of, I mean, technology was there, but it was way ahead from everybody else. And then it was put in FERC order eventually, and it's now common ground for everybody. But because they put it in early on, majority of ERCOT's fleet is frequency responsible and can provide support, each one providing just a little bit. Nobody has to reserve headroom. Nobody has to have, forego the revenue because of that capability. But now they all support the grid, and ERCOT needs to buy less reserve for frequency control. So that saves costs, and this capability is already there, built into entire fleet. Now ERCOT has 66 gigawatts. At the time they started, they only had like maybe a few thousand megawatt of inverter-based resources. So having this capability built in early on and spread across multiple resources also saves costs on having to implement it through market and requiring it as a reserve.
Well, and the point there is that it was required early on, even maybe ahead of the technology, kind of building on what Ryan is saying. Song, any thoughts on this question in terms of, the word SAR has been thrown around, and
Yeah.
what are your thoughts on this?
Yeah, I totally agree with Ryan and Julie. I just want to probably just summarize there's a point a little bit. I think one thing is regulatory hurdles, right? Regulatory frameworks, often lag behind the technology advancements. So existing regulation may not adequately address the capability and potential of grid forming waters, leading the uncertainty and barriers to widespread deployment. That is the thing. And also the thinking the interconnection standards, you will never have that. Standardize the interconnection requirements and the protocol. And I think that's a critical for the seamless integration of the grid forming inverter into the existing power system. So that's two things. If we can put some effort, on that, and then so we can make this move forward more faster.
Great, thank you.
So if you've ever been a panelist where I've been a moderator before, I tend to do one thing, and we're going to do that now. And that is, if there were one thing, one bullet point that you could provide primarily policymakers, regulators, the people who are making the decisions about not only implementation, but recovery of costs, what would the one piece of information that you would want them to know, the sound bite, right? If you're think TikTok, if you could do a TikTok video and a 30-second sound bite, I would love for each of you to address that sound bite that you would like them to walk away with from this discussion that would help the most in furthering the technology. Let's go Song, Julia, Ryan. How's that?
Okay. So my word, like, promoting the grid forming technology require continuous research, testing, and the collaboration among the stakeholders, including the utilities, technology developers, research, and the policymakers. I think by advancing our understanding of grid forming water technology and addressing key challenges, we can unlock its full potential to transform the electricity grid toward a more sustainable and resilient future.
Thanks, Sung. PG is doing a lot of work to front that for the benefit of the other utilities. So we look forward to seeing how that's going with you. Julia.
Yeah, I would say as you are approving or as you are reviewing transmission upgrade proposals, ask the question, have you looked into grid forming benefits? Have you looked at if these resources come in and bring grid forming capability, do you actually need this transmission assets? And how much can you save by deploying grid forming capability? I'm done.
Thank you. Ryan.
Yeah, I think my one-liner is it's no longer an R&D project. It's commercially available. It's zero cost, and the root of the moving it forward stems in the interconnection requirements. As simple as that. And I don't do TikTok, so I get 37 seconds or something. I did promise Travis I would make a reference to it. This whole concept reminded me of the Robert Frost poem, the road not taken, right? Two roads diverged in a wood, and I took the one less traveled, and it made all the difference, right? And we're kind of at that point, right, where if we keep going down this path, we're headed towards a weakening grid. We know we'll need eventual system upgrades that are very expensive. And so it's like you're driving on this wonderfully smooth road and you turn and you're staring right at the Wasatch Mountains and you have the most rickety gravel road you've got to go up to get over them, right? The alternative is you hop onto I-80 and it's got some windy turns around it and it goes over a mountain pass, but the end goal is you're in Park City, right? So like there's my WEC specific analogy. Right, the status quo is a lot more painful than the minor complexities and twists and turns that we'll have by moving towards adopting grid forming at scale. And I think most industry experts, if not all industry experts around the world, will tell that same story.
I love that ending for this discussion. Two roads diverged in a wood. That one, I grant you, will be used multiple times after this by other people who have listened in and participated in the call. I want to thank each of you so much. There's so much to learn on this subject. We can't possibly get to it in even just a couple of discussions, but I think that we have made leaps forward in order to help educate people on this, which primarily I think is what needs to occur in order to get to a place where it can be a technology that people are going to utilize and look at more rapid deployment of the technology itself. So I'm going to pass things back to Travis and allow him to close us out, but great discussion. Thanks so much.
Good deal, Brian. You did hold true to your promise for a Frost reference, so appreciate that closing.
And Travis is a Robert Frost aficionado, I learned through planning this,
Yeah,
so that's a fun fact about Travis that we all
I
know.
went to school very close to his home. So um, again, I want to just echo Chris's thanks to our panelists, Ryan, Song, and Julia. Appreciate you coming on to share with our stakeholders, and Victoria and Chris, appreciate you leading the conversation here. I'm going to point to next month, April 3rd, from 11 until 12. We'll be having the continuation of the reliability in the West discussion, where the IBR discussion will continue, but in a little bit of a different format. We'll be talking about IBR registration. So mark your calendars for that. It's April 3rd, 11 o'clock Mountain Time. Look forward to seeing you all then. And thanks again for joining us, everyone.
Thank you. Bye.